Hello everyone. I'm going to be looking at 2D arrays right now. They're just a variant on our normal dynamic arrays, but they can add to a little bit of confusion for a lot of people. They can be difficult to get your head around, but hopefully this will make a bit more sense once we get looking at the actual code itself. 2D arrays, sometimes you actually want two-dimensional arrays, as in not just I want a straight list of numbers, but maybe I want a width and a height. So for example, a bitmap, I might want a certain number, a width and a height to make a picture. So that intuitively makes sense, and you can come up with a lot of examples where you would actually want a two-dimensional array. And it may not just be for pictures, it might be other things as well. But the key is that it involves doing a little bit of extra fandangling with our arrays. So first of all, let's have a quick look at what we're looking at. We're looking at 2D arrays for about 20 minutes, and then we're going to do a fairly extensive in-class, quote unquote, exercise here. Then after that, the next presentation is going to be a bitwise operators presentation, and then we're going to look at building and linking. Fairly rudimentary, fairly cursory view of building and linking, but and pre-compilation instructions with that. And then we're going to, after we do all of that, I might do another review of pointers, and then we'll move on to file I/O. So a two-dimensional array, it can be done a number of different ways, but essentially what you want is an array that works in multiple different directions. So I may have an array that looks like, hopefully my pen's going to work. Let's fix my pen here. All right. That would be a one-dimensional array. Well, what if I keep on doing that over and over and over again? Well, that is one of many, I can do that one of many ways. So let's break this down into different approaches. So the first approach is I make an array, I make an array, I make an array, I make an array, and for each one of and then I make an array of pointers to these arrays, essentially. So I make each row one after the other. That would be this step right here. And then I shove them all within the main array, this array of arrays, if you will. So for each individual row or column, depending on how you want to view things, for each individual row in my array, I will make a one-dimensional array. They're all going to be the same width. They're the same number of elements. But I keep on making these arrays, and then I stick a pointer to each of those arrays in my main array, this AA my nums. That would be the arrays of arrays approach to doing this. That requires something like a for loop in between to actually make each of these, rows or these arrays within the array. So I make the overall array, and then I have something like a for loop, some kind of loop to make each one of the individual arrays that go inside of it. The static approach might seem a lot easier to you guys. It's this thing right here. I'm going to make an array 4 by 5. So it will be presumably 4 elements across, 5 up. It's sort of arbitrary. These don't actually have space. So I'm going to go 4 elements across and then 5 up in this particular array. Now that might seem easier, but it's also static. A static array, I cannot change. I can't make it a variable size. I can't change, well, in all cases, I can't change it later, but I can't get, information from the user asking them how big this array needs to be. It is going to be one size and one size only. And we'll also see another little weird quirk about static arrays. And then we have a pseudo 2D approach to it. Now, the pseudo 2D approach to it is actually just computer scientists getting all cutesy, I guess, if you want to look at it this way. The idea is, well, that is a two-dimensional array, right, up here that we have. But what if it doesn't actually have to be like that? So what we could say is, well, this is 5 different elements, right? And the next one would be, so this is 0 to 4, and this would be 5 to 6, 7, 8, 9. This would be 10 to 14, and this would be 15 to 19. What if I just pretended it was a two-dimensional array, make a giant 20-element one-dimensional array, and just carve it up on the fly? Figure it out as I go. So instead of actually me trying to figure out making arrays of arrays and all that kind of fun stuff, instead I just make a very, very big array and let the math do all the work for me. And we'll see that as an example as well. They are all effectively equivalent. They're not actually equivalent. The syntax is going to be different, but they all solve the problem in a very similar way. And they all have pros and cons, but there are multiple different approaches or multiple different ways of getting to the same kind of solution. So I'm going to go through each of these things in code. So hold on one second. So let me go over to our code. Here's lecture 14 for the two-dimensional array. This is in our shared code repository that you all have access to. So 2D arrays in the shared repository. Well, first of all, let me point out for this exercise, I'm going to quote unquote hard code some numbers. I'm going to make a constant. Notice I'm not putting the number 4 and 5 everywhere because when I want to change that number to 17 and 42 or whatever number I want it to I change it one place and it works. So I'll just let the cat out of the bag here and build this, show that it actually works. Okay, it works. Let's make that 9. And everything should still work as it did before. In fact, let me just run this like I did before. Well, I didn't do it before for you guys, but I ran this code before. So if my mouse was actually working, here we go. Boom. Very big arrays or big-ish arrays, and it's going to be harder to read these, but this is a 9 by 5 array, 3 of them actually. So I'm going to do this one more time, but instead of a 9 by 5, I'm going to go back to this 4 by 5. All right, let's build it again. And let's run it. If I can left click my mouse trackpads. Okay, so here is a 4 by 5. Notice I have 4 elements across and I have 5 rows. 5 rows, 4 columns. That's what I'm doing for each of this. Now this is going to be my one-dimensional array, quote unquote. The giant array that I'm going to slice up myself. This is going to be my two-dimensional array right here. And I do believe, if I'm not mistaken, this is my static two-dimensional array. I don't even know why I have another one down here, so we'll have to look at that why the code is there. So here is what my plan of attack here is. I am going to make 3 different arrays. First array I'm going to make is a static array that has a width and a height. Those cannot change, they're constant. Second array, I'm going to make a one-dimensional array, just a single normal call to malloc. But notice it's going to be width times height in size. So 4 by 5 or 20 elements. The other one has 20 elements too, but they're 5 by 4. They're laid out in a two-dimensional way. Versus this thing here is just 20 elements in an array. And then the third approach is I'm going to make an array for each row. That's why height, right? Every single row, the total height would be the size of my array. So for every single row in my array, I'm going to have a pointer into this array here. I have an array which holds a pointer to other arrays. Okay, I want to make sure that my call to malloc actually works, so that's why I have that assert there. And then below, I'm going to so since I have made this row, these series of rows, the pointers to each row array, if you will. This is my call to malloc. I make it's an array of int pointers. Each of those int pointers is going to point to an array. And so it's a two-dimensional array in that way. So once I've made that sort of overarching structure for each row of my array, I am going to make a brand new array, which is the width, if you will, and I put each one of those in each individual row of my array. So I made an array of pointers, and I make an array of elements for each row. I essentially make each row and I hook them into the main array. Here is me Here I am, actually, I should say, grammatically correct. Here I am using two for loops, and what I'm going to do is I'm going to put the number, the index, if you will, or actually the total index or the total number that I have into each element of each of the three arrays. So I have an I have a J, and what I'm going to be doing is I'm going to stick this, I have this value index, sorry, here's the value index. It is the number, however bit wide this array is, multiplied by how many rows I've done. So if I have done, let's take, for example, I'll put this down, row 3, uh, column 2. All right, so at column 2, if you look at how this algorithm is actually working, column 2, that's our J value. So J is equal to 2, J is equal to 2, and I should need an equal sign here, and I is equal to, well, I'm in row 3. Okay, notice what would that actually end up being? So our width itself, we went back up to here, we look at our width. Our width is 4. Okay, there's 4 elements per row. Let's go back down to my code. So this index itself is equal to, well, it's 4 times the value I, 4 times 3, 12. And then I'm also, what column am I on? I'm on column 2. And so what I would expect to get is 14. 12 plus 2, the 14. That's the index that I would be in at row 3, column 2. Row 0, column 0 is value 0. Row 0, column 1, the next element, is 1. Column 2 is 2. Column 3 is 3. There is no column 4 because there's only the width is actually size 4. Then I go to the next row. It would be row 1, column 0. Row 1, column 1. Row 1, column 2. Over and over again. And that's how I'm getting these indices. If you want, we can actually just have a quick look at what this actually looks like. Hopefully. And that left mouse button every time. Okay, going to recompile. Yeah, so here we go. 0, 0, and this is row 0, column 1. Row 0, column 2. Row 0, column 3. Row 1, column 1. Column 0. Row 1, column 1. There you go. And so all we're doing is counting out the indices in this array. Okay. That's all I'm doing with this part. So I get this IDX value, and I'm going to stick it in the appropriate array position for each of the arrays. So I can go into row I. This is the row I, column J. I'm going to put the value index. For the dynamic array, it's row I, column J, put in the index. And for the dynamic 1D array, it's, well, remember it's flat, so I say how many rows over I go. So I times the number of rows over I went, plus whatever column I'm in. And that's going to be my index. They should do the exact same thing in all 3 cases. Okay. After that, I'm going to play around with this a little bit more, and this is where things get a little hairy. I'm going to call I made 3 different functions. One for a one-dimensional array, one for a two-dimensional array, and another for our static two-dimensional array, because even I found out there's something quirky going on with the static two-dimensional array. Static arrays, they work interchangeably with normal arrays. You just get a pointer to the array, unless they're 2D, and then things get a little wonky. So we'll see that in a second. Okay, so and this is me actually just playing around with my values. I'm going to get rid of it, but this is me testing what the heck is happening with my static array and why it wasn't working with a straight double pointer. This is me playing and debugging things myself when I'm making this demo initially. I'm going to get rid of that, but here we go. I'm going to go to this particular, I can hopefully should be able to jump to go to definition F12, and here I am. I'm in the definition of a one-dimensional array. Now, I could do 2 for loops and then try and just print out every element in my array. Or that, yeah, that seems like a reasonable thing to do. Or what I could do, the other approach, and also to still do the math. The other approach, you'll notice, is I might be able to let the math do the work for me to figure out what column I'm in, what row I'm in, based off of a particular position. So if I'm at position 12 in my array, this is not width 12 or column 12 or anything like that. This is position index 12 out of 20 positions. How do I know what column I'm in, what row I'm in? Well, I can figure out the X position or the column based off of using the remainder again. I know that a column is exactly, in this case, 4 elements wide. And so if I take 12 and then I modify, let's see, the width should be 4 elements wide. So if I take uh, if I take this 12 and I divide it by 4, what would I end up getting? I should get a remainder 0. And so this is at position 0. And if I did this, so I can even do, let's do 13 just to make it hopefully a bit easier. Here is me doing 13, 13. Okay, so this should be equal to 1. And if I go down here, then the width is 4 again. So if I divide 13 by 4, what do I end up getting? Right? I should end up getting 3. So I'm at row 3 and at column 1. You don't actually need this, but let's have a look at this. So the real size of my array is the width times height. That's a one-dimensional array. And I could just use a single for loop, just walk down every single element in my array. That would be nice. That would be easy. It prints out fairly nice. Except I want to also see to make sure that I understood how to get the actual row and column. And so here I am getting the row, sorry, the column here, or the X position. Here's me getting the Y position, or the so the Y position would be the row, right? So the X and the Y, putting in parentheses, and then the actual number that's going to be in there. So at the end, when I know I'm at the end of a row, so if the width, if I mod the width, if that's equal to, well, with the width minus 1, as in I'm never going to be at position 4, but I could be at position 3. That's the end of my row at position 3. If it was totaling 4, I had a row had a width of 4, so there's a grand total of 4 different columns, then the very last one would be at position 3. That's what I'm looking for. And if I get into that situation, I just want a new line just to make it look nicer. All right. Oh, this is me doing, that's why I had the same thing pop out twice. So I'm going to comment it out. This is why I had what we had earlier. Here would be another way of doing the same thing with a two-dimensional array. I'm going from 0 to height, and I'm going from 0 to width. And so for each row, I'm going to print out everything, and then I'm going to do a new line. That's this line here. So I print out everything in the row, do a new line. Print out everything in the row, do a new line. And I do that however high or however many rows I have. And for each of those positions, I can say, oh, I know where it is. It's at position J plus whatever, however many widths I've done. So the height multiplied by however wide this thing is. This will give me the exact same array as what I did above. They are exactly doing the exact same thing with the array, just two different approaches. Finally, okay, so then let's look at, here is our two-dimensional array. This is our dynamic two-dimensional array. It is int pointer pointer. It's a pointer to int pointers, if you will. It's an array that holds int pointers, and each of those int pointers points to an array. So it's an array of arrays. I have a width, I have a height, and to get to an individual elements, I do the exact same thing as before. Notice what this is actually doing. So let me put this in a comment. AA nums at position, at position J, position I, that's going to be equal to plus I dereference. Well, that's going to be one of my pointers. I'm looking into one of my pointers. And oh, wait, if I go and plus J to this thing, and let's make sure my parentheses are correct. And that should do it. So 1, 2, 3. All right. So this is me moving my pointer position over, I positions, dereferencing it. That'll get me a pointer. It's a pointer. It's a array of pointers. So that gives me the pointer at position I. And then I say, okay, what's at position J in that new array? So that is why AA nums actually works. AA nums IJ is get me the pointer at position I. Oh, now get me the value at position J within that other array. So get me the array, now get me the value at position J in that new array. I go down row by row, I print out each row, make a new line, print out each row, make a new line until I run out of rows to print out. So that's me doing a two-dimensional array with a pointer, an array of arrays. And here is the weird one, because Lord knows I had trouble figuring it out. I had to look it up myself because I don't do static arrays this way very often. Most of the time, if you need a two-dimensional array, oftentimes you'll just need a dynamic two-dimensional array. It's not going to be some static value. And so, or at least especially if you're not passing that two-dimensional array to another function, that's where it gets really wonky. So for a two-dimensional array, the one little kicker is it should look and act exactly like our dynamic arrays. In fact, it almost exactly does. The one difference is you need to know how wide each of those rows are. Just the nature of how a two-dimensional array works. And so as a result, I need to say what the size of the array I'm going to is. This is essentially an array of pointers, an array of int pointers, and that array is text width in terms of size. That would be something I'm not going to be even asking on the exam, but if you ever needed to look or pass in a static array to to a function, this is how it would end up looking. So just like before, the code itself is identical to what our two-dimensional array looks like. They look identical to one another. The only difference is this parameter coming in, I have to say how wide this thing is. That's it. But they act and behave in a very similar way because that's actually what's going on under the hood. There's just some extra precautions taken by C when you're making something with a static array where it says, well, I know how big this is. Don't be just moving things around. So here I am making a two-dimensional static array or printing out all the values in my two-dimensional static array. Again, let me recompile it one more time, just in case, and let's look at what we have. Here is my one-dimensional array that I'm pretending is two-dimensional. It has 20 elements, 0 to 19. Here is my two-dimensional array. It is a dynamic two-dimensional array. It has arrays 0 to 19. Here is my static two-dimensional array. It has elements 0 to 19. In fact, these two, the body of both of these functions are identical to one another. The only one that's different is this one where I have to do a little bit of math to make it work. All right. So with that being said, let's see if there's other things I wanted to bring up before, and otherwise I'll move on to the next lecture. So that's mostly what I wanted to go over. We have three different approaches to doing a two-dimensional array. Try one on your own. So in fact, let's give this as an exercise. Let's make a 2D array of floats. Let's do this, an array of char strings. Or C string. So let's call it a C string like we've been so we're consistent. That would be An array of characters. That's what we've already been doing. If I needed an array of these strings, what would I do? How would I do it? Well, that's actually where this comes in handy. So try that out. That would be my suggestion. So one of the approaches, and what I'll do is for the next video, so we'll stop it now. You try this exercise out. Try to make an array of C strings, um, an array of 10 C strings, and make an array, a 2D array of, and let's say a 6 by 3 array of floating point numbers. When we come back next time in the next video, I'll show you the code that would actually do this, just so you can compare your work. But make sure you actually try it, because otherwise it's not going to really stick in. All right, and with that, I'm going to take my leave of you. Thanks, guys.